Right, so this is a theory paper, a complexity theory paper. What is planning? In planning, we have different domains, and what a planner does is consider just one of them, and then if you feed it an initial state and the goal, it tries to go from the former to the latter. We can formalize it with a set of propositional state variables, and then the initial state and goal are subsets of that, where the goal needs to be satisfied, but a superset of the goal is also fine. And we might have a set of actions. Now this is just a set. Okay. And then the domain assigns to every action its meaning, consisting of a precondition, an add effect, and a delete effect. Meaning the precondition has to be true if you want to apply the action, and if you do that, add is added and delete is deleted. This is an example. The table on the left should be self-explanatory, and the table on the right also defines the domain, where a plus means that the action adds the variable, a cross means that the action deletes the variable, and a circle means that the variable is a precondition of the action. This initial state is empty, and if the goal is x and z, we can solve it as follows. We start by applying action A that has no preconditions, and then C, for example, B, A, and we've reached the goal. Notice the yellow dot without the circle, meaning that the variable is present, but it's not a precondition of that action, nor is it deleted. So that is planning, and domain learning is the opposite. Given a plan, calculate a domain, an initial state, and the goal. And this could be useful because writing domains manually is tedious and error prone. And if we can automate that process, we can use it for planning, especially if we want to reuse a domain with different initial state and goal. But is a plan a sequence of actions or a sequence of actions and states, in the sense that you see the actions and also after each action the state that you reach by applying it? The first variant would be a fully unobserved world where you know what happens but you don't see anything of the effects. And the second would be a fully observed world where you see the full description of the world at every point in time. So an example of the fully observed case is this, where the input of a domain learner could be this. And let's see. Right, so the only thing you don't know is whether coffee is actually in the goal. It probably is, because otherwise the goal is empty. But in theory, the goal could be empty. And then you could, for example, learn this domain. Or you could learn this domain. The difference is just that beans could be a precondition of press button 2 or not. So there can be multiple possibilities. And a computer, of course, doesn't have any associations with the words beans and water and so forth. So this is, non-trivial to a computer. Now, the fully observed case already has a publication by my co-authors at AAAI. And now we look at the fully unobserved case. Then the input is just press button 1, press button 2, pull lever. But that could just as well be ABC. So you have very little information. And then there could be all sorts of domains that you could think of. So it seems that you can do very little. But to give you a first flavor of what you can do, if you have a longer plan and you see something like this, that every time press button 2 is followed by pull lever, then it might be that press button 2 adds a precondition of pull lever, because it seems to enable that. So even without seeing a state, you might be able to plausibly infer something like this. But then still, if you suppose such a variable exists, you still have two options. It could also be deleted by pull lever or not. Okay, and now I will talk about plan justification, because we want to formalize this type of domain learning, and without further definitions we cannot yet do anything, because still any domain is basically possible. In particular, we have no way of strictly inferring preconditions. Now, a justified plan is a plan every action of which is needed, loosely speaking. This definition has two variants, and it depends on the domain. This is an example of a plan in a domain. And I will argue that it satisfies exactly one of the two variants. So I will explain these definitions of justifications by this example. It's well justified. Well justification, it means we cannot remove an action. If we remove action A, then the precondition X of action B fails. So removing A results in an invalid plan in this domain. If we remove the first occurrence of action B, variable Y will be false, so action C will have a false precondition and the plan breaks. Similarly, if we remove action C, then B, the second occurrence of B will fail. And if we remove the second occurrence of B, the goal is not going to be satisfied at the end. So if we remove any single action, the plan is not valid anymore. This means that the plan is well justified. But this is not an example of a perfectly justified plan. Not every action is needed in the sense that we can remove actions if we remove multiple actions. We can remove a set of actions, for example, the first occurrence of B and C, resulting in a valid plan. Okay, morally, a justified plan is a plan that is reasonable. So suppose you want coffee from the coffee machine again, and you need to scan your card. You could also scan your card twice. Maybe the machine doesn't complain about that, and it still works, but there's no reason to do that, because scanning your card once is enough to get coffee. So scanning your card twice could be a valid plan, but not a justified plan, and also not a perfectly justified plan. So now we can formalize some interesting complexity problems. Given a plan, that's just a sequence of actions, so a sequence of symbols, find the domain and initial state and goal such that it is well justified, or such that it is perfectly justified. And then we prove it's in P for well justification, and it's in co-NP for perfect justification. It makes sense that it becomes a bit harder because this perfect justification was about sets of actions and not about single actions. We also believe that this is tight, and we have some more results because we were now asking for any domain, but it could be that you don't want the domain to be overly complicated. It might be that you know there exists a domain that is not of size 1,000,000, but of size at most 100. And then you get this decision problem. And surprisingly, even though you have more restrictions on the domain, the complexity goes up. So deciding whether such a domain exists for well justification is NP complete. And we have hardness with a constant K. And for perfect justification, it's in sigma P2. That's the highest complexity of the paper. It corresponds to formulas with an exists for all quantifier. And we again believe it's tight, though for such a hardness proof, we're gonna definitely need to have K variable. K is then not constant anymore in the hardness proof. An example, find domain in which this plan is well justified. Okay, you need to start somewhere. Maybe there's an action added by A, and then you could start building the domain like this. But then it's not well justified because you can remove this action B and it still works equally well. So this is not a good domain. Maybe B also adds something, then B cannot be removed again. So the domain already becomes a bit larger. And similarly, this is not good enough because now C can be removed from the plan, so the plan is still not well justified, and so on. This is still not good enough because we can now remove the second occurrence of A and the plan would still achieve the goal. So you can think a bit and then you need to do something with the delete effect. There might be a variable that's added by A but deleted by E, so it needs to be added by A at the end. And now the plan is well justified. In fact, you can even remove variable X again. The bounded case can be formulated here as find me the domain with its minimum number of variables, and then yeah, you can do this, for example. As you see, it's a bit trickier. And that's the end of the presentation.
Questions? Patrick?
So I take it you're doing propositional domains here, and as you said, the actions are just symbols. So if you were given structured actions of name parameters, and you want to, let's say, restrict yourself to something like strips model, which means that the effects will be kind of uniform between different instantiations, that would make it would add constraints on what are possible domains. And I'm just wondering what's your intuition. Would that make the decision problem harder or easier?
So I think it can't make the decision problem easier because it's more general. And yeah, this is definitely one of the main directions of future research, and the complexity probably stays the same in the number of cases, because when you guess something, you can probably also guess it with those constraints. But yeah, it's future research.
Another question. So, no, the goal is playing a role here in the learning formulation, right? So the notion of well justification, the goal plays a role.
Yes.
Isn't that strange, okay, that for learning a domain you are using the goal? So you can do model learning without using the goal at all. So the question is, in what sense the results are about a complexity of a particular method as opposed to the problem itself of learning the model?
The goal and initial state, I think, really don't matter, theoretically speaking. In the paper, they are not really there. There we, argue that without loss of generality, the initial state is the initial state is empty, and the goal, you can model the goal in the domain by having a final action whose precondition is the goal. But I think that you can't have the goal given if in the unobserved case, because that would already give away something about the number of variables, for example.
Any question? Yes. So,
thank you for the presentation. Have you also considered extending this to take multiple actions, multiple plans, and generalize a single domain for all of those traces?
Right, that's another direction of future research. And again, the intuition is that it's going to be similar, because you can already try to think of artificial constructs where you combine several plans into one, separating them with dummy actions. So that the dummy action can just change the goal of the previous fragment into the initial state of the next fragment. So sometimes it really doesn't matter, but
Wouldn't you perhaps sort of factorize some of those variables and make sure you don't necessarily double up and recreate additional, but you create the more compact domain?
sorry, can you speak up a bit?
Couldn't you create a more compact domain instead of just concatenating the plans and using new variables each time?
There's a difference between the plans and the domain, right? So even if you concatenate the plans in this artificial way, the domain that the algorithm learns could still use variables for several segments. Does that make sense?
okay. So I think we have to move on. Okay, thanks.